Hello, everyone. My name is Abigail Glover, and this is the bonus project for the spring 2023 semester for Fluid Mechanics with Dr. Ozbay. As you can see, I already have my workbench pulled up, and I don't have access to my project 3 anymore, but the handout does specify that we are allowed to use the same meshing processes from project 3 for this project. So I've already done the recreation of that process before starting this video. So I have my geometry with the green check, my mesh with the green check, so we are ready to dive into this project. So what I'm going to start by doing is duplicating this system. So now that we have our duplicate system, we can go ahead and just jump straight into setup. I'm going to go ahead and rename this real quick. For this project, we're doing 5 flows in Inviscid and then 4 specific Reynolds numbers. So for the sake of this, I will start with the Inviscid flow just so we have our basis to go off of. We're going to do double precision with 4 solver processes. So once we have our CFD solver pulled up, you can see my mesh here. I'm just going to go ahead and start by setting up my models. I'm going to change this from viscous SSTK omega to Inviscid, since that is the flow we're looking for. I'm going to go into my materials. Now for each of my cases, I left my density, whatever was system generated, and then just calculated my necessary velocity based on that. So we are good to go with the 1.225 here. We're not going to change anything here, but if we wanted to, we could double check what kind of fluid we're looking at. We can see it's air, so that is good to go as well. And then for our boundary conditions, the only thing we're really going to look at for this case is going to be the velocity. So I am going to set my velocity as 0.15. And what I noticed in this project is with the different velocities that you pick, it actually changes where on the y-axis our final graph comes out. So I messed around with the values a bunch, and 0.15 is what ended up working for me to get that starting point at 1. After that, we're not going to change anything internal, sorry. For the outlet, same thing, we're not going to change anything here. So after that, I'm going to go ahead and just go to results, residuals. I'm going to change my residual to 1e to the -6. I'm going to make sure everything is that value. And then we're going to go here to methods. For Inviscid, we're going to do simple. And presto. And then we can leave it second order upwind. From here, we can go ahead and double check our reference values. We're going to compute from the inlet. We've got our velocity there, and our reference zone is going to be the surface body. From here, I'm going to go ahead and initialize. And once my initialization is done, I'm going to go ahead and run the calculation. So now that our calculation is complete, we can see that it converged around 1,066 solutions, 1,066 iterations to get our solution. So from here, we have 2 ways to get the necessary data for the project. One way is to go over here and do an XY plot. We're going to look at the pressure coefficient for the cylinder. And with that, we can see our Inviscid flow, similar to that of the handout. Now, the exception is we do have these 2 lines, just because it is going around a cylinder. From here, we need to extract this data. We have our pressure coefficient here on the y-axis and our position in meters on the x-axis. So what we can do to pull that is we can go over here, click Write to File, and write, and then we can go whatever file we want to save it. So I will just name this Inviscid Flow CP versus X data. From here, if I were to go to my files, I can see that I have it here. And when I double click that, I would export it to Excel. I'm going to trust it. And there is my data. So now from here, if we go back to our workbench, I'm going to just go ahead and update my results and show you the second way to get the data. In the second case, instead of looking at the pressure coefficient and the X value for the location, we're going to examine the pressure coefficient versus theta for the distance. So I'm just going to double click my results here. Once we have it pulled up in Post, I am just going to start by adding a plane. And then from here, I'm going to add a polyline. We're going to intersect the cylinder. It's going to be plane one. There we go. So we want that intersection with the plane and the cylinder. As you can see, it's three-dimensional, even though we drew it in two-dimensional. This is exactly where we want to pull our data from. So from here, we're going to go ahead and go to expressions, and we're going to create our two expressions for our pressure coefficient and our theta. I'm going to start with theta. And it's going to be my equation. The great thing about this is you can go in and edit your equations if you notice that they're wrong. And then my additional comment on this is that we do want to make sure that we are carrying the units, because if we don't carry the units, when we hit apply, it's not going to update the output unit for the chart. So now we have our theta expression. I'm going to go ahead and add pressure coefficient expression. And here we're going to have pressure. And then that's going to be divided by 0.5 times our density, which was system generated, which was 1.225. And then our velocity that we used was 0.15, and that's going to be squared. Now, I did just say we need to carry our units, so we're going to go ahead and add those in. So now when we hit apply, I'm going to just put parentheses around. We get a variable, which is what we want because the pressure coefficient is non-dimensional, so it's not going to have a unit, which means that we did all of our units correctly in this equation. So from here, we can go to variables. We're going to hit new. We're going to start with theta. And we're going to pull it from our expression list. Apply, and we're going to do the same thing for the pressure coefficient. So now we have our expressions, we have where we're pulling the data from. We can go over here to chart viewer. And we're going to insert a chart. This is going to be our CP versus theta for Inviscid flow. Flow. And here we're going to go to data series. We are pulling from the polyline. Our x-axis is going to be our theta. And then I already know based on the handout, our minimum value is going to be 0, whereas our maximum value is going to be 180. From here, our y-axis is going to be CP, and our minimum value is going to be -3, whereas our maximum value is going to be 1. From here, we can apply, and we can see our chart. And you can see it's a little bit below 1, so what I can do here is I can actually go back to my CFD solver. I can go to my inlet, and I can adjust my velocity. I'm going to make sure I change it here and in my reference values. And then I'm going to initialize and calculate again. So from there, once we've updated that, we do need to remember to go in and update our expression with the updated velocity. And as you can see, that has moved closer to that initial value of 1, and it's still maintaining its minimum at around -3. This does take some fine tuning. I've had to mess with the values quite a bit. In some of the runs, that 0.15 works, and some of them you have to bump it up a lot, but this is the general idea behind this. You want to find that velocity that hits that sweet spot at 1, make sure your equation matches it, and then you're good to go from there. From here, you can export your data by going into your chart and clicking export. From there, you do the same thing. You go to the location that you want to save it to. And we'll save it as Inviscid flow, theta, CP versus theta. Can X out, and if I were to go here, I now have that data saved here. It would be the same thing. I would just double click and export it to an Excel sheet. I'm going to go ahead and update, but once that's updated, we should have all green check marks, and that means that our Inviscid flow is complete. From here, I can go ahead and duplicate my main project 3 meshing system again. And I'm going to double click setup. Same thing, we're going to do double precision for processes. And once we have it pulled up, we're going to go ahead and just start from models. Instead of doing viscous SST K omega, this time we're going to do K epsilon. From here, we're going to do enhanced wall treatment with pressure gradient effects. Click OK. And then we're going to start defining our parameters. Now, in this case, I am going to start with the first Reynolds number that is in the handout, which is a value of 1 × 10 to the 5th power. So what I did personally to get that Reynolds number was I kept density and viscosity the exact same as they are in the system, because that's just less things for me to have to change when I'm doing this. It makes it much easier when you're doing this multiple times in a row. And then the only value that I did change was my velocity. So in order to get that Reynolds number with the given viscosity and density, I calculated a value of 1.460734694. I'm going to copy and paste that in our reference values because we will need that again. So I'm just going to go ahead and apply that here. We are not changing anything in our outlet, our symmetry, our wall, all of that is staying the same. From here, we're going to go to reference values. We're computing from the inlet. You can see that it does cut off some of our number. It rounds, that is fine. And then we're going to make sure that our reference zone is surface body. From here, I'm going to go into results and just make sure that my residuals are all 1e to the negative 6. And okay. From here, we are good to go ahead and initialize. Once our initialization is done, we are good to run the calculations. I'm just going to do 1500. So our calculation is now complete. We made it to 158 iterations before it converged, and we are going to do the same thing we did for the Inviscid flow to get our plots. So from here, you can see that it starts at 1 again, comes around, and then it kind of tapers off. So from there, we can go to our and we can do the same thing. We can write to file to pull that data. From here, we go to results, and we do the same exact thing we did for the Inviscid flow. We're going to go to expressions, new, we're going to create our theta expression. And we're going to create our pressure coefficient expression. And then for each case in our pressure coefficient equation, we have to update it with whatever velocity we used for each specific Reynolds number. And we're going to put our units in parentheses. Make sure we get a variable. Perfect. We can go ahead and set up our variables. And from here, I'm going to go ahead and add my plane and my polyline. Perfect. From here, we can go ahead and insert our chart. We're going to pull our data series from the polyline. Our X is going to be our theta again. And our Y is going to be our CP. I'm going to go ahead and update my range. Y. So now we have this data in our graph form. From here, we can export this data to Excel. And that concludes that first Reynolds case. For each of the following 3 cases, our 2.6, our 8.5, and our 3.6 times 10 to the 6, it's going to be the same exact process where we go back into our workbench. We duplicate our project 3 meshing so that we have the same consistent meshing for each one. And then we go and we change our setup. From here, technically, because we have that Reynolds, it's going to be the same setup as that for our other Reynolds numbers. The only thing we are changing is then the velocity. So I will show one more case. I will do the 2.6 times 10 to the 5th. And then the following two cases are just duplicating that. So from here, I'm going to duplicate my 1 times 10 to the 5th. You can duplicate the meshing or this one because the setup will be the same other than the velocity. So from here, though, we would go into setup. All right, now that I have the CFD solver pulled back up, we can see that it has the same settings as our previous example with the 1 times 10 to the 5th. We've got our K epsilon, our enhanced wall treatment, our pressure gradient effects. We are good to go there. Our materials, nothing's going to change. We are keeping the density and viscosity consistent with what the system is generating. Now we are going to go into our inlet, and for this case, the 2.6 times 10 to the 5th, we are going to change the velocity to what we calculate to get that necessary Reynolds number. So from here, I calculated 3.7979100204. So from here, we're going to hit apply. Nothing's going to change here. All of our results, our residuals are saved. And that's what makes it so much easier to copy from that one. You can always copy from the project 3 meshing, but copying from that first case, we know all the settings are staying the same. We're just changing our velocity. So from here, I can go ahead and initialize. We've got our initialization. I'm going to double check my reference values to make sure that we are calculating from the inlet and everything carried over. From here, we can go ahead and calculate. So for this case, our calculation converged at 154 iterations. We can go ahead and go to plots, XY plot. We're going to go over here to pressure coefficients for the cylinder. And there is our lovely plot, pressure coefficient versus position. From here, we can write to file. And we can save this as our CP versus X. RE equals 2.6 times 10 to the 5th. And then from here, we can go ahead and open our results. And because we copied from that first Reynolds number, we already have our plane, we already have our intersection, we have our expressions, and we have our variables. So all we need to do from here is create a chart. Our data series is going to be our polyline, our X is going to be our theta, and our Y is going to be our pressure coefficient. Now, the only thing we do need to worry about is we do need to go in and change our expression for our coefficient of pressure, and we need to update our velocity. So for this one, we're just going to retype it. Apply, and now we've got those correct bounds. So from here, we can export our data. We go back into the chart. We can export here. From here, we've got all of our data saved. For the sake of this video and time, I'm going to go ahead and jump into how to combining how to combine the charts and to combine the data in Excel. But as I stated before, we have our Inviscid flow. We have 2 of the 4 Reynolds number cases. From here, you would just duplicate your first Reynolds number case. You would go into CFD Solver. You would change your velocity. And then when you go into post, you just need to make sure that you carry that velocity over into your coefficient of pressure equation. From there, you can export your data from both, and we can open them up in Excel. So to start creating the graphs, I'm going to go ahead and open up one of my data sheets. Doesn't matter which one. I usually start with the Inviscid, and I'm just going to keep everything nice and organized. So I'm going to delete things that are unnecessary. And make sure you label everything as you go. So now we've got our Inviscid flow here. This is for theta versus CP. But I'm going to go ahead and just click Insert, Chart, and it automatically generates this chart here for us. Now it's kind of ugly, so we can go ahead and we can mess around with the settings. I'm not going to go through that in this video, but I'm going to go ahead and do that off camera just so that it's easier to look at while we put in all of our data. Okay, so I am back with my much more organized chart. You can see here I added axes titles. I readjusted my axes so they looked a little nicer. They weren't in the scientific notation. It is going up to 180 degrees. It just doesn't show the 180 here, but then I also have my legend and my title. So from here, I'm going to go ahead and just move this back up to the top so it's easier to keep track of. And then we are going to go to our files. Now this is for the pressure coefficient versus theta. I personally made 2 charts. I made one with pressure coefficient versus theta and one with pressure coefficient versus location in meters. So for this, I'm going to stick with theta values just to make sure all of my values are staying consistent. I'm not mixing meters with theta. So from here, I'm going to go ahead and just open up my file for my Reynolds number for 1 times 10 to the 5th. From here, I'm just going to highlight my data. We're going to copy it and bring it over to the other Excel. I'm going to go ahead and label so that I keep track of everything. Here, it lets us, we're going to paste it. There we go. So then we're going to go here, we're going to select data, we're going to add. Our x is going to be our theta. And our y is going to be our CP. And you can already see that that has popped up on our chart. So then from there, we would just go back. We can go ahead and close out this file. And we can open up our Reynolds number for 2.6 times 10 to the 5th. And then we're going to go back and add this data. And we can see it's popped up here. You would pull the data for the other two. This is just showing these three cases, but that is how you would export that data to Excel to create your chart for your pressure coefficient versus your location with theta. It would be the same exact process for our pressure coefficient and our location in meters. We would just pull from that data instead. So from there, that pretty much wraps up the essentials of how to complete this project and all of the steps that I took to complete it. Thank you so much for watching and have a wonderful day.